Okay, great. So I'm just going to start here sharing some images with you. So I'm really happy to be able to talk to you about this really amazing astronomical discovery I was a part of last year, but also tell you a little bit about how one gets to be an astrophysicist and what you actually do once you're there. And so, as Lisa mentioned, this image here is actually a collaboration of an artist at Sonoma State University and members of the LIGO and Virgo scientific collaborations that worked out that a signal came from crashing neutron stars, not too far on an intergalactic sense from our own galaxy. So let me just start off. So who am I? I'm a professor in the physics department at a university in California, but I actually started out in Canada. I'm from Calgary, Alberta, and I did a math and physics degree in Canada too, but my connection to Wisconsin comes in when I did a doctorate degree in Milwaukee. So I spent 5.5 years in Wisconsin, Milwaukee, working on learning about neutron stars from gravitational waves. And then I also spent, after I did my degree, some time doing research, which means I worked at, for example, in Germany near Berlin. I spent a couple years there at a place called the Albert Einstein Institute studying gravitational waves. And then I spent a couple years in Oxford, Mississippi at the University of Mississippi in their Center for Gravitation and Cosmology. And then about 5 years ago, I started as a professor here in California, which means today I work not only alone on gravitational research, so modern science is done in a very interactive way, traveling around the world, talking to people, working with students. In the top right there are two of the students that were co-authors on the discovery of a neutron star merger as they worked in my research group, and other members of our research group are shown in the other two pictures. So this is a big group of folks working together and contributing to science as undergraduates. So as some of you move on from high school, if you start a college degree, you can find not necessarily gravitational wave physics, but all sorts of really interesting ways to contribute to knowledge and learning, even as you're only a couple years into your degree, like our students were able to do. So I should also mention another connection to your high school. So my husband, here shown in a photo of my family, is an alumnus of your high school, and so he is now a software engineer here with me in California. And in the same time as all this research has been going on, I also have two little boys that are growing up, and so this is a part of life as a scientist. So let me go now to what I talk about when I say I'm learning about gravity. So probably most of you are familiar with things falling down, and one of the biggest first ideas of gravity was that the orbit of the moon, so this is the Earth-Moon system seen from NASA's Mars Reconnaissance Orbiter in 2016, and we now know from Newtonian physics that the moon falls around the Earth in an orbit, which is how we see the moon change in our sky as it makes its journey around the Earth, as the Earth itself is orbiting the sun. And both of these effects are governed by gravity. Our modern picture of gravity, though, is not just this Newtonian picture anymore. So now we have Einstein's general relativity, which is summarized in the sort of idea that matter, like masses like suns and planets, tells space and time itself to curve. And the motion of things in orbits is them moving through this curved space-time. So something like the Earth or the sun distorts the space around it, so a passing smaller object gets deflected. And you might see this sort of three-dimensional thing given an idea as a sort of a slice through the three-dimensional space, showing a stretching. And just like if you roll a ball on a curved surface and it will tip around, if you've played mini golf, you'll experience this phenomena. Our planets get their curved orbits because they're traveling through this curved space-time. So now most of this sort of gravitational effect isn't very strong. We only notice it on Earth really when we're trying to do things like GPS measurements, which are really precise clocks, so they measure time so precisely to make GPS localizations that we need to correct for this warping of space and time around the massive Earth. Gravitational effects get strongest when you have a lot of mass in a small area. So our sun is something like 100 times as big across as the Earth. But if you wanted to compress all of that mass of the sun and more into something about the size of the Minocqua area, you would get an object called a neutron star, which we observe in radio and X-ray measurements. We're not quite sure how big these are, which is one of the problems I study, but we know that they're comparable to the size of a small city. And then a neutron star is matter's last stand against sort of a collapse to an object we call a black hole. So this same amount of mass, more than the mass of the sun, would make a black hole that is quite small. This is roughly to scale. And I've shown here a sphere depicting the horizon of the black hole, which is this sort of spherical point of no return, where nothing, not even light, can escape. You may see pictures of black holes where people kind of cut a cross-section through. And if you tried to make a map of a region of space around a black hole, you'd find that the space is so distorted that you have to make you have to make a kind of a funnel instead of a flat map to show everything that's going on. And in this sort of funnel, the horizon is just a line instead of a sphere at the bottom of the funnel. And that's the point of no return for light, people, spaceships, and everything else. Larger black holes are larger, but something 62 times the mass of the sun is still small compared to the Earth. It's about the size of maybe Iceland there. We also know that there's a larger black hole in the center of our galaxy. We see that because we observe these stars shown here in the purple, blue, and green orbiting around a dark point in space in the Sagittarius constellation. And, well, these little stars are refusing to orbit right now, but hopefully if I give them a chance. So these are observations, and the top right is the date, the year that these star positions were observed. And over the last decades, we've seen these stars looping around this dark point in space and measured by their orbits the mass of the central black hole of our galaxy, 4 million times the mass of our sun. So that's a bit bigger than our Earth. So we now can kind of ask, well, just like our picture of orbits comes from curved space-time, there's some implications for what happens when you look at mass in motion. So back to the moon passing by the Earth, the pull that I feel from the Earth and the moon will change as the moon changes its relative position compared to the Earth. But I won't know that that change has happened until the signal has time to propagate to where I am. This is a principle of relativity, that nothing can travel faster than light. And what that means is that the space-time around orbiting objects, the change ripples out like a wave. This is what we call a gravitational wave. So here at the center here are 2 little black hole funnels that are going to orbit around and stir up the space-time around them sending out this pattern of ripples that carries energy away from the two objects, and then they fall together and merge. This movie was made by another student at Cal State Fullerton. Now, we measure these tiny ripples with a system of lasers. As the ripple goes through, it changes the lengths between things, it changes space. So we take a laser and we shine it down two long interferometer arms, and as the distances change, a little bit of light escapes this system, it's called an interferometer, and we measure the change in light to record this precise distance change. And it's something like the distance change we measure is the relative size of a human hair compared to the nearest star, Proxima Centauri. So it's a very precision measurement. It's a lot more of a complicated system than I showed there. We have these 3 interferometers with 4-kilometer long arms in Washington, Louisiana, and in Italy, and complicated vacuum systems and suspensions and engineering and systems control loops, computer science, optics, all sorts of fields coming together to make one of the most precision measurements ever made. This was our first signal. That thump is the ripple of 2 black holes colliding, like you saw in that movie a few slides ago. And from the way that ripple hit the detectors, we figured out that it was 2 black holes, each about 30 times the mass of the sun, 36 plus 29. This movie will show the bending of light around the black holes. It's a slowed down movie to show 0.2 seconds in time as the black holes collide. And they settle down into a mass of 62 solar masses, which those of you who are quick with addition may have noticed that some of the mass has been lost. That's the mass that went out in gravitational wave energy. From the strength of this signal, we figured out that it was 1 billion light years away and has been traveling to us for 1 billion years at the speed of light. Then in August, we got the second signal. Now this signal was a bit different. It started low, below it's easy to hear in the data, and slowly built out, not over 0.2 seconds, but over tens of seconds. So you'll only start to see it in the central detector, Livingston, which was the most sensitive, as a bright line ramping up through the center of this animation. The final pitch of neutron stars merging is more of a whoop than a thud. That's because they're lighter, so they have a higher frequency pitch to their signal. And this is a visualization of what might have been going on with the neutron stars merging. As they orbit, they distort each other, they collide, they fling off a bunch of dense matter, which forms all the elements of gold, platinum, and other heavy elements in our universe. And then they collapse to a black hole with a torus of matter around it that launches a jet of gamma rays and throws off material to glow in a red and blue light that was predicted actually by astronomers even before we were able to observe the first one. But in this instance, we recorded a gamma ray burst from the Fermi satellite less than 2 seconds later. And then we were able to map the sky with gravitational waves to figure out where it came from. And telescopes found this new source of light in a nearby galaxy. So before just the galaxy, afterwards that new little spot of light in the upper left corner. Watching this light appear and fade over the course of days gave us a lot of information about the radioactive decay of elements and how matter is created by these sorts of processes in our galaxy to form the elements we see on Earth today. So this is just some of the stuff we were able to learn from this observation. We found it's in a galaxy only 130 million light years away, the closest gravitational wave observation, and the first time we've seen light from a gravitational wave source. Before this, we predicted that neutron star mergers produce gamma ray bursts, but this is the first time we were able to confirm that. We saw them produce heavy elements. we measured, because the gamma ray and the gravitational wave signal arrive so close together, that light and gravity travel at the same speed to a couple seconds in 130 million years. And this is a new way to measure the universe expansion and make limits on the properties of neutron star matter. So that's all I had to talk about. I wanted to leave time to answer any questions you all have about just this astronomy, or just science, or being a scientist in general. So thank you.
Well, thank you, Dr. Reed. If we could get back to see you, that would be fantastic. But does anyone have any questions? We can speak to her through this microphone. I have one. In the scientific community, there was a lag between when the discovery came and when you announced the discovery. How was that? How hard was that to remain quiet when there was all kinds of inquiries coming around?
So I think this neutron star merger, someone called it the worst kept secret in astronomy, partly because we were sharing the data with all these telescope partners under agreements of confidentiality, but there were hundreds of facilities around the world checking to see if they'd seen the thing at the same time. This was an unprecedented opportunity to make multi-band observations of the first time we'd ever seen this event. Maybe, we don't yet know how exceptional this opportunity was. Hopefully it's something common, but it may have been a once in a lifetime chance, hopefully not. But so we were telling everyone we could, this is an amazing thing. We've never been able to see this before in the sky. Please point your telescopes at it. So I think the author list of the papers had thousands of people working together to do this. So we didn't have published results because everyone wanted to double check that things were correct and make sure the analysis was correct before we announced the findings publicly. But a lot of people knew broadly what was going on. So,
yeah. Does anyone have anything else? Any other question? You have a question.
Sorry, I didn't quite hear that.
There's a question over here.
Do you think which do you think is going to die first, the sun or the earth?
The question was, what do you think is going to go first, the sun or the earth?
Well, depends what you mean by go. So we know that the sun is going to possibly engulf the earth as it transitions to a red giant in about 4 billion years. But what the earth will look like after 4 billion more years, that's roughly how long it's been around so far. So it's been it took a long time to get to its current configuration, and it's hard to say what's going to happen in another amount of time to just the way Earth will be over a billion-year timescale. Sorry if that's not quite the question you asked. I'm having a little trouble understanding what people are saying. Maybe someone could talk to the laptop directly to repeat questions.
Yeah, why don't you tell me? The question is, how many people were on the team that did the research for this latest gravitational wave discovery?
Good question, Bryce.
Right. So the research team there's the LIGO and Virgo scientific collaborations. So each of these involves dozens of universities and research institutes around the globe. The LIGO collaboration mostly is based in the US and the UK and Canada and Mexico and Korea and India. But there's a lot of collaborators in other institutions. And then Virgo is a consortium focused on the Italian detector, but LIGO and Virgo work extremely closely together. And so that's most of Europe working on the Virgo detector. And so altogether, that's over about 1,200 people that work more than half their time on this. And then there's a lot of people that have research focuses that aren't entirely directed at gravitational waves, but are participating in offering expertise for specialist tasks. So some of the Neutron Star stuff, we brought in people that were part of the collaboration but don't usually spend a lot of time on it to spend focused time on this and contribute to this research. So thousands of people.
What's the daily life of like an astrophysicist? Like, you just solve math equations for fun, or like, what do you do?
Yeah, so it depends on the astrophysicist. So I have colleagues who do a lot more solving math equations, like they like pens and notebooks and sitting in coffee shops kind of thing. Most of what I do is less mathematically oriented. Aside from confirming the mathematical framework of things, I spend a lot of time implementing it in code. So numerical computations tend to be more efficient for messy real-world situations. So we have sort of a mathematical framework of setting up what equations describe the system. Some people work on developing that mathematical framework better. Most of what I do is analyzing data and translating mathematical frameworks and supercomputer simulation results into the implications for data analysis to understand, what's the astrophysical case we do. So I do a small amount of, pen and paper calculations, mapping out results. Spend a lot of time reading papers that other people have written. I spend a lot of time writing computer codes and running it on computer clusters, writing papers describing what I've done, reviewing results of colleagues in the collaboration. And then I also, as a professor, I spend another chunk of my time teaching classes. So I have a part research, part teaching and university service job now. So I also teach students in Introduction to Astronomy, classical electrodynamics, and some other subjects. But in practice, I spend a lot of time sitting in front of a computer.
Do you believe in aliens?
So I believe statistically, given the number of planets we observe, and that Earth doesn't seem to be extremely exceptional, that it seems just likely, given the vast scale of the universe, that aliens are out there. I'm not convinced by any evidence of their particular instances of aliens I've seen, but the universe is so huge. There's more stars than grains of sand on every beach in Earth. We see like more than half the stars I forget the number, but between 20 and 50% of the stars, like our sun, have Earth-like planets that we've been able to observe just by staring at them in our galaxy. So it seems very unlikely that there's no other life anywhere in the universe. It's just, the universe is really big. It's hard. It's 5 light years to the nearest star, hundreds of thousands of light years across the galaxy. That's a speed limit that makes it really hard to figure out what's going on in distant places.
When you teach your classes, do you just teach gravitational waves or do you teach other subjects?
I didn't quite hear the last sentence. When I teach my classes, do
you teach just gravitational wave classes, or do you teach other subjects?
Yeah, so I teach classes from independent study with gravitational wave research students and nuclear physics research students to like a general education course on Introduction to Astronomy that's just open to students from dance majors to business majors to everyone just wanting to get university general education. Then I teach a lot of classes for physics majors And most of what I focus on in the undergraduate curriculum is learning about electricity and magnetism. It turns out the equations that we use to describe electricity and magnetism have a lot of similarities to Einstein's equations in certain limits. So the techniques we use to understand gravity come from techniques that were used to understand charges and magnetic fields.
Where do you think the future of astrophysics is going?
Could you repeat that one again?
Where do you think the future of astrophysics is going?
So I think one of the exciting things to have been a part of is to be here in a new field of astronomy. So, when we're feeling creative, we compare it to Galileo looking through a telescope for the first time. And Galileo's telescope was about as powerful as a common pair of binoculars, if any of you have binoculars for looking at wildlife or anything like that. That can match the power of Galileo's telescope. If you looked at Jupiter with your binoculars, you'll probably be able to find its moons with careful observation. And that first observation of Galileo was just scratching the surface of everything we've learned about astronomy, like learning that the universe is expanding, learning that we are one, not only moving around the sun, but our sun is one star of billions in our galaxy. Our galaxy is one galaxy of millions billions in our universe. So I think what excites me most about the future of astronomy is we're learning how to see the universe with new senses, really, things that we're not used to. And I think the unexpected discoveries that will pan out over centuries are going to be something we really have very little idea of now, because we just have no way to know what the universe is like in gravitational waves in the broadest scope. So seeing what surprises await is sort of the exciting part of the future.
Can you think back to your high school self and tell us just how you decided to go into what you went into, what things influenced you? Were there other things you were thinking about and then you settled on this? Can you give us give kids any advice about how to make those decisions?
Well, so when I started high school, I wanted to write science fiction, and I liked reading, I like reading science fiction novels. So I found that ones that I thought were really cool had really interesting, planetary systems and aliens, and I wanted to figure out how that stuff worked so I could make up like reasonable, plausible ideas. And then I really got caught up in the science of it and just learning about the universe. So when I started, by the time I was through high school, I was taking a lot of science just because I was curious, but I wasn't sure whether I wanted to do biology or physics or math or whatever. So I kind of did both, and then in university, I talked to people, and it looked like it would be easier, because I was very indecisive, to try starting in physics and going into biophysics. There wasn't a comparable route. If you start in biology, it's harder to go into physics. So I did physics, and I did math, because math is like the Swiss Army knife of science. And then I just sort of found professors that were working on interesting things, and just worked with people I thought were doing interesting projects, or where I thought things could be useful. And I think the real hook was, in undergrad, most of what I did was not new research, but sort of just this idea of understanding something new. But the real hook doing my degree was that as a scientist, I had an opportunity to figure out something that no one on Earth had ever realized before. And that's a pretty addictive feeling, that you're the first person to figure something out, even if it's just a little implication of some equations or a new method. It's really fun to find something new like that, and so that's what's kept me going on this path.
Many scientists believe that our universe is a computer simulation. What are your thoughts on that?
Yeah, so I've seen a few of these ideas, the sort of speculative ideas that the universe is somehow a computer system simulation, that maybe there's hints of that in the way quantum physics works or something like that. A lot of these I find to be kind of cool ideas, but not so testable or practical. So I don't think it's something that a majority of scientists spend a lot of time thinking about, but it's fun to read articles about them.
Okay, can you hear me?
Yes.
Okay. I understand you had some connections with the University of Wisconsin-Milwaukee, which I think is just amazingly cool because that's my home school. And how did that all happen, and how did UWM become involved in the LIGO project? Because everybody in Wisconsin who was interested in these things was like, hey, UWM's involved, yay, Panthers.
So I ended up at UWM because, so I was doing college at the University of British Columbia, and I still actually, I left this out, I was taking a class in gravity, in theoretical gravity. It was sort of an honors undergrad upper division thing. And I'd handed in a project, and the professor, she said, well, what are you going to do after you graduate? And I said, I have no idea, I don't know. And she said, well, have you thought about doing research, because this project was pretty good. And she had worked with a professor at University of Wisconsin-Milwaukee, who she said this is a great person to work with, you should apply to their research group. I'd actually missed a bunch of deadlines, but UWM was still offering them. So it was pure luck that they were there. And then UWM has a Center for Gravitation and Cosmology. There's one of the largest research groups contributing to the LIGO scientific collaboration. So they were an epicenter of gravitational research. So I didn't actually get involved in the collaboration while I was at UWM, but I really got introduced to the gravitational community there, and then continued.
When the neutron stars collided, would any of the materials have any radiation on them remaining from the collision? All the matter was sent through.
So what he's asking, when the two neutron stars collided, was there radiation remaining there?
Right,
On the
so
materials?
neutron stars colliding definitely had, so we observed emission from this one system, so they stirred up the gravitational wave sort of before they collided. The collapse to the black hole lacked gamma radiation. That's one of the most high energy photons, so light can be radio waves, infrared, optical light, ultraviolet, X-rays, gamma rays. So we saw gamma rays right off. We've seen an X-ray glow from this system that is only starting to fade now, about half a year afterwards. The optical glow took about a day to brighten, and then has slowly faded over a few weeks, so it was radiating light. And there were detections in radio too. That's from the outflows and the jets crashing into the interstellar medium amidst radio waves. So it radiated everything. We have observations across the spectrum with all our observatories. We being the scientific community as a whole, not just something I'm directly involved in.
What do you think about string theory?
Did you hear it? He wanted to know what you thought about string theory.
String theory. So I think how to say this? So I think it's this fundamental problem with our theory of gravity is that it doesn't play well with quantum mechanics and quantum field theory. And so I want my picture of the universe to fit together nicely, and I think string theory is sort of an interesting way to do that. It has a lot of beautiful mathematics, actually, from string theory that I actually find more compelling when it gets applied to some other problems. So if you collide ions together in a earthbound collision laboratory, we can use some of those mathematical techniques developed for string theory to understand what's going on in this sort of quark-gluon plasma. So there's sort of cool applications of string theory, and I think it's really still an open question if it's really the right way to connect gravity and quantum theory. So coming from the gravitational community, string theory is sort of a way that particle physicists tried to add gravity into the particle physics model. There's also a way where gravitational physicists took gravity and tried to quantize it. It's called loop quantum gravity, and they both interestingly give consistent results in some ways. So anyway, this is a sort of an open question. I'm probably getting too technical, but string theory is neat, and I don't know if it's got any unique grasp on truth, but it's a fascinating set of mathematical techniques.
So, Dr. Reed, we have about 5 more minutes before the end of the hour. We have one last question, and that is, why do you think this discovery is important, and how will it affect us?
What was the second part? Sorry?
How will it affect us?
Yeah, so really, the importance of this discovery comes down to fundamental physics, and that's the sort of try to understand how the world works without necessarily understanding immediate practical applications. And I think this is something that humans have done over the centuries with varying sources of support. From back in Galileo's day, it was sort of rich nobles. Now we have scientific programs funded by governments. The sort of just blue sky, how does our world work research. And so what we learned was a huge amount of just fundamental open questions we had about how our universe worked. Right now, I don't yet see the direct, now we know that neutron stars crash together in a galaxy 130 million light years today and output the gold that's in our everyday objects around us. We know how that those materials were made now, but it doesn't change our day-to-day lives yet. But the interesting thing is, as I said, gravity, the theory we use today, is now something constructed just to understand why light moved in different directions the same way. This is Einstein's the Michelson-Morley experiment that launched, in some ways, the modern understanding of relativity. And now we use all those results for precision measurement in GPS satellites, which is who would have guessed that was ever going to be relevant for that sort of practical thing? So I don't see how this affects day-to-day life yet, but I wouldn't be surprised that 100 years from now, our grandchildren are going to be saying something really cool that came out of this kind of discovery.
Well, I'd like to thank you, Dr. Reed, for spending this hour with us here at Lakeland.